A silent graveyard for galaxies exists in the depths of space. This is the Interstellar Graveyard, a concept that forces us to rethink how the universe lives and dies. We will trace the entire journey of these celestial giants, revealing the hidden forces that guide them to their final rest. By the end, you will understand the ultimate fate awaiting our own Milky Way. What cosmic killers are responsible for extinguishing billions of stars? And how does a galaxy's own black hole seal its doom? What does it feel like to watch an entire universe grow old? Galaxies breathe in a slow, cosmic rhythm, inhaling gas to forge new stars and exhaling the remnants of old ones. This cycle defines their vibrant lives, but it does not last forever. We can trace the entire existence of a galaxy, from its chaotic birth to its quiet end. In the primordial darkness of the early universe, immense clouds of hydrogen gas and the mysterious pull of dark matter began to coalesce. These were the raw materials, the cosmic nurseries where gravity sculpted the first grand structures. Over billions of years, these swirling masses of gas collapsed, ignited their first stars, and settled into the majestic spirals and glowing ellipticals we recognize today. A galaxy's vitality is measured by its star formation rate, the pace at which it converts its vast gas reserves into new, brilliant suns. A young galaxy is a stellar factory, bursting with energy and light. But this furious pace cannot be sustained forever. Internal forces begin to slow the engine. The supermassive black hole at its heart can awaken, its powerful jets heating the surrounding gas and preventing it from cooling to form new stars. External threats also loom. A galactic collision, while spectacular, can violently strip away a galaxy's gas or push it all into a feeding frenzy at the center, effectively ending widespread star birth. This is the onset of cosmic senescence, a gradual fading from a blue, star-forming youth to a red, aging retirement. This inevitable decline makes the final destination we are about to explore all the more profound. To understand the graveyard, we must first appreciate the long and winding road that leads every galaxy to its gates. This quiet, final state is the Interstellar Graveyard. It is not a single, marked location you could point a telescope toward, like a city on a cosmic map. Instead, think of it as a condition, a phase of existence that galaxies enter when their vibrant lives are over. A galaxy in this graveyard has lost its ability to create new stars. Its vast reservoirs of cold gas, the raw material for stellar birth, have been exhausted, stripped away, or heated into uselessness. What remains is a population of aging stars, slowly burning through their final fuel. The brilliant blue-white light of massive, short-lived stars is gone, replaced by the dim, ruddy glow of long-lived, lower-mass stars, the stellar equivalent of embers cooling in a cosmic hearth. You will often find these retired galaxies adrift in the immense, empty tracts of space we call cosmic voids, truly isolated in their old age. Others exist as what astronomers call red and dead galaxies, sitting silently within the crowded metropolis of a galaxy cluster, surrounded by neighbors but no longer interacting with them in any meaningful, creative way. They are the faded giants of the cosmos. This concept fundamentally reshapes our understanding of the universe. We are forced to see it not just as a place of violent birth and brilliant life, but also one of inevitable, profound quiet. The Interstellar Graveyard is the ultimate retirement home for celestial structures, and its very existence hints at a universal story with a final, quiet chapter for all. The journey to this cosmic graveyard is a story of migration, a slow drift guided by invisible forces. One of the most dramatic paths leads galaxies into the crowded hearts of immense galaxy clusters. Here, a galaxy does not simply drift in peace. It plunges through the superheated plasma that fills the space between galaxies, a thin but incredibly energetic gas. As the galaxy moves at tremendous speeds, this intergalactic medium acts like a powerful, constant wind, violently blowing away its own reserves of cold star-forming gas. Astronomers call this brutal process ram pressure stripping. Picture a dandelion seed head blown by a gust of wind, its delicate filaments scattered into nothingness. In a similar way, a galaxy's lifeblood is stripped from it, leaving it gasping and unable to create new stars. The galaxy's spiral arms, once traced with glowing stellar nurseries, fade into a featureless red haze. But not every galaxy meets such a violent end. Some reside in the profound isolation of cosmic voids, vast, empty regions where neighbors are few and far between. In this quiet solitude, a different fate unfolds. These galaxies are not robbed, they simply exhaust their fuel. They continue forming stars at a leisurely pace, slowly but surely consuming their finite supply of gas until, one by one, the last stellar embers ignite and fade. The great star-making factories fall silent, not with a bang, but with a slow, cosmic sigh. This migration, whether through violent interaction or quiet exhaustion, is an inexorable process spanning billions of years. It is a universal journey that every galaxy, including our own Milky Way, is destined to make. But the story does not end with the galaxy's visible stars and gas. There is a deeper, invisible force at work, one that has guided its entire existence from the very beginning. This second mystery revolves around dark matter, the universe's hidden skeleton. Every galaxy, including our own, is embedded within a vast, diffuse sphere of this enigmatic substance. You cannot see it or touch it, but its gravitational pull is immense, acting as the primary anchor that holds the galaxy together. This dark matter halo dictates the galaxy's motion through the cosmic web, steering it toward clusters, into filaments, or leaving it adrift in a void. It is this invisible hand that ultimately controls the galaxy's journey to its final rest. When a galaxy falls into the crowded core of a massive cluster, it faces a gravitational onslaught. The collective pull from the cluster's own immense dark matter can violently tear away the galaxy's protective halo. This process, known as tidal stripping, is a cosmic amputation. Once this invisible scaffolding is severed, the galaxy loses its gravitational grip on the clouds of pristine hydrogen, gas that linger in intergalactic space. It can no longer accrue this fresh fuel to spark new generations of stars. The galaxy's fate is sealed not by what is taken from its visible body, but by the theft of its invisible soul. Its star-forming engine, already sputtering, grinds to a permanent halt. Yet a robust dark matter halo can also be a shield. For a galaxy living in a quieter neighborhood, this invisible cocoon provides stability, allowing it to hold onto its gas and continue forming stars at a gentle pace for billions of years. The delicate interplay between the galaxy's visible matter and this mysterious dark component is a decisive factor in its lifespan. The strength and integrity of this unseen structure determines whether a galaxy meets a violent, abrupt end or fades away in quiet solitude. So the question becomes, what happens when even this protective halo is not enough to save a galaxy from the most destructive force in its own core? At the heart of this cosmic extinction lies a process astronomers call quenching. It is the final, decisive shutdown of a galaxy's stellar engine, the moment its great star-forging furnaces are permanently extinguished. This quenching is not one single event, but a slow, cosmic suffocation. Primary culprit is often the galaxy's own supermassive black hole. When this sleeping giant awakens, it becomes an active galactic nucleus, a powerhouse of unimaginable energy. Vast jets of radiation and particles erupt from its poles, flooding the entire galaxy. This is not a gentle warmth, but a violent, scorching blast that heats the reservoirs of cold gas, preventing them from ever cooling and collapsing into new stars. In more extreme cases, these winds can blow the gas clean out of the galaxy, leaving it barren and gasping. But the black hole is not the only killer. In the crowded downtown of a galaxy cluster, a different kind of violence unfolds. Here, galaxies whip past each other at incredible speeds, their gravitational fields constantly tugging and distorting one another. This relentless bullying, known as galaxy harassment, shakes a galaxy to its core. The orderly orbits of its gas clouds are thrown into chaos, disrupting the delicate conditions required for star birth. Sometimes the interaction is even more direct. A galactic merger, while spectacular to witness, can be a terminal event. The collision funnels vast amounts of gas directly into the central black hole, triggering a catastrophic feedback loop that sterilizes the newly formed galaxy. All of these mechanisms conspire to create the silent, red populations we find in the interstellar graveyard. They are the cosmic killers, the forces that transform vibrant, blue spirals into the faded red giants that drift in eternal quiet. The beautiful spiral arms of a galaxy are not permanent. They are a fleeting signature of its vibrant youth, and their erasure marks one of the most profound transformations in the cosmos. Many of the silent, red galaxies we find in the interstellar graveyard have lost all trace of their spiral structure, becoming smooth, featureless balls of ancient stars known as elliptical galaxies. How does such a dramatic metamorphosis occur? The answer often lies in a catastrophic event, a galactic merger of epic proportions. When two spiral galaxies of roughly equal size are drawn together by gravity, they do not simply pass through one another. Their intricate structures are violently torn apart over hundreds of millions of years. The gravitational tides from this cosmic dance pull and twist the delicate spiral arms into long, streaming tails of stars and gas. For a brief, brilliant moment, this chaos triggers a final, furious burst of star formation. The collision compresses vast clouds of gas all at once, igniting a firestorm of new suns. But this stellar baby boom is a last gasp, not a new beginning. The violence of the merger funnels immense amounts of gas directly into the supermassive black holes at the galaxy's cores, awakening them into ferocious activity. The resulting energy output heats or blows away any remaining star-forming fuel. As the chaos settles, the two galaxies coalesce into a single, new object. The orderly, rotating disk of a spiral is gone forever, replaced by a random, swarm-like orbit of stars, the defining characteristic of an elliptical galaxy. This new entity is redder, older, and structurally simpler. Its identity has been permanently rewritten, its fate as a resident of the graveyard sealed by a collision that erased its past and extinguished its future. Yet the most profound deaths may be the quietest ones, far from the chaotic downtown of galaxy clusters. In the vast, empty suburbs of the universe, another kind of graveyard resident exists. These are the isolated galaxies, and they face a fate not of violence but of slow, cosmic starvation. Imagine a single farmstead on a vast, empty plain, cut off from all trade routes. It can survive for a long time on the supplies it has stored in its barns, but once those are gone, there is no way to get more. This is the essence of strangulation. An isolated galaxy is its own closed system. It continues to form new stars at a steady, gentle pace, faithfully converting its internal reservoir of cold gas into new suns. For billions of years, this process can continue, a quiet, solitary existence. but the galaxy is disconnected from the cosmic web, the vast network of invisible filaments that channel fresh, cold gas throughout the universe. No new fuel is arriving. The galaxy is living entirely on its savings with no income. Slowly, inevitably, it consumes the very last of its star-forming gas. The great stellar factories do not explode or get torn away. They simply fall silent one by one as the final raw materials are used up. The brilliant blue glow of young star clusters fades forever. What remains is the dim, red light of long-lived, aging stars. The galaxy's once distinct spiral arms, now devoid of stellar nurseries, become faint and washed out, their structure slowly blurring over eons. It does not explode or collide. It simply fades, becoming a red ghost drifting in the immense, silent emptiness between the clusters. This lonely end is a stark contrast to the dramatic mergers we see elsewhere, a reminder that in the cosmos, silence can be just as final as fire. Deep within the graveyard, we find the oldest residents of all. These are not the faded giants of a later era, but cosmic fossils, galaxies that lived fast and died young when the universe was in its infancy. Astronomers call them red nuggets, and they are some of the most mysterious objects in the cosmos. Imagine a galaxy as massive as our own Milky Way, but compressed into a volume 100 times smaller. These are incredibly dense, compact powerhouses that formed their entire quota of stars in a single, furious burst of activity over 12 billion years ago, when the universe was less than half its current age. Then, just as suddenly, they shut down. Their star-forming engines were permanently quenched, and they have drifted through cosmic time ever since as red, dead relics. Their very existence poses a serious challenge to our models of how galaxies are supposed to grow. The standard story suggests that galaxies start small and build up their mass gradually over time through mergers and steady gas accretion. But red nuggets were already fully formed and retired when the universe was young. How did they assemble so much mass so quickly? What cosmic force could have been powerful enough to stop their prodigious star formation in its tracks, effectively fossilizing them for all eternity? The leading theory points to their supermassive black holes. In these dense environments, a feeding frenzy at the galactic center may have unleashed such immense energy that it blew away the entire galaxy's remaining gas supply in one catastrophic event. Another possibility is that they were so efficient at forming stars that they simply ran out of fuel at a record-breaking pace, burning through their cosmic reserves in a blink of geological time. Studying these red nuggets is like opening a time capsule from the early universe. They offer a pristine glimpse into the first cycles of galactic life and death, showing us that the journey to the graveyard began much, much earlier than we ever suspected. The true power of these galactic thermostats lies in their ability to sculpt the cosmos from within. A supermassive black hole, even one that is quiet, anchors its galaxy with an immense gravitational presence. But when it awakens and begins to feed, it transforms into an active galactic nucleus, one of the most energetic phenomena in the universe. The process is not a gentle one. As matter spirals into the black hole's event horizon, it forms a superheated disk of plasma, and this colossal engine can blast out jets of radiation and particles at nearly the speed of light. These jets pour energy directly into the galaxy's heart, flooding the vast reservoirs of cold gas. Think of a pot of water placed on a blazing fire. The heat prevents the water from condensing, keeping it in a gaseous state. In a similar way, the energy from the active nucleus heats the galactic gas, preventing it from ever cooling down enough to collapse under its own gravity and ignite new stars. This is feedback in its most critical role. a self-regulating mechanism that can quench a galaxy's star-forming potential for billions of years. In some cases, the effect is even more dramatic. The outflowing winds can be so powerful they do not just heat the gas, they blow it clean out of the galaxy entirely, stripping it of its future. This creates a profound connection between the very small, the intense physics at the edge of a black hole, and the very large, the ultimate fate of an entire galaxy. A single, relatively tiny object at the center can act as a switch, either preserving a galaxy's vibrant life or condemning it to an early retirement in the interstellar graveyard. How does this invisible thermostat know when to turn on? And could our own Milky Way's quiet heart one day awaken with such world-ending force? This final erasure is perhaps the most violent end a galaxy can face. Deep within the heart of a massive galaxy cluster, a lone spiral drifts too close to the central, dominant elliptical galaxy, a true cosmic leviathan. The difference in their gravitational pull is immense. As the smaller galaxy approaches, the force of gravity on the side nearest the giant is vastly stronger than the force on its far side. This difference, a tidal force, begins to stretch the galaxy. It is no longer a cohesive island of stars, but a piece of cosmic taffy being pulled apart. First, the most loosely bound stars on its outer edges are plucked away, forming long, shimmering streams that arc ahead and behind the galaxy's core. Then, the galaxy's own reservoir of gas and dust is violently stripped. Within a few 100 million years, a blink in cosmic time, the galaxy's identity is completely erased. Its stars are not destroyed, but they are scattered, torn from their galactic home, and cast adrift into the emptiness between galaxies. This scattered starlight becomes what astronomers call Intra-Cluster Light, a faint, ghostly glow that permeates the entire cluster. It is the collective phantom of all the galaxies that have been devoured. This process, tidal disruption, creates a different kind of graveyard resident. It is not a faded galaxy, but a dissolved one. Its material becomes part of the cluster's atmosphere, a permanent, diffuse memorial to a structure that no longer exists. This demonstrates the ultimate power of the graveyard. It does not only accept the quietly retired or the merged, it also claims those that are violently, utterly dismembered, proving that in the cosmos, even an entire galaxy can be unmade. Astronomers have a simple but profound map for charting the lives of galaxies. It is called the color magnitude diagram, and it reveals a universe cleanly divided into two distinct populations. On one side lies the blue cloud, a region teeming with spiral and irregular galaxies actively giving birth to new, hot blue stars. Their light is dominated by the brilliant glare of stellar nurseries. On the other side rests the red sequence, a stark band of galaxies that glow with the steady, ruddy light of ancient stars. These are the retired giants, the ones that have ceased forming new suns. This is not a random scatter of points. The existence of this sharp divide, this cosmic bimodality, tells us that a galaxy's vibrant life and its quiet death are two very distinct states of being. There is no messy middle ground, no long period of gradual fading. The transition from the blue cloud to the red sequence is a galaxy's final, definitive journey into retirement. This movement is a one-way trip. Once a galaxy joins the red sequence, it almost never returns to the star-forming chaos of the blue cloud. The forces that push it there, whether a voracious black hole, a violent collision, or the slow exhaustion of its fuel, are simply too final. Every massive galaxy we see is destined for this fate, destined to one day cross that great divide and take its place among the silent, red citizens of the interstellar graveyard. What does this cosmic map tell us about the ultimate fate of our own galactic home? The final, quiet state of a galaxy hinges on a single, critical resource, its cold gas. This is the raw material for star formation, the cosmic fuel that powers a galaxy's vibrant light. For a galaxy to truly die, this fuel must be taken away or rendered useless. Astronomers face a compelling puzzle known as the missing gas problem. When they compare active, star-forming galaxies with their quenched, red counterparts in the graveyard, they find a stark discrepancy. The retired galaxies possess only a tiny fraction of the cold atomic and molecular hydrogen that their lively cousins hold. The question is simple and profound. Where did it all go? The investigation into this cosmic theft reveals a gallery of suspects, each with a distinct method of operation. One culprit, ram pressure stripping, acts with brutal efficiency in crowded galaxy clusters. As a galaxy plunges through the superheated plasma between galaxies, this intergalactic wind can scour its disk clean, blowing the delicate clouds of star-forming gas away into the void. It is a direct and violent robbery. Another suspect works from the inside. When a supermassive black hole awakens, its tremendous energy output heats the surrounding gas halos to millions of degrees. This scorching bath prevents the gas from ever cooling down and condensing into new stars. The fuel is still technically there, but it has been permanently locked in a state too energetic to be of any use, a cosmic treasure trapped behind an impassable wall of heat. Sometimes the galaxy is an accomplice in its own demise. During a major merger, vast reservoirs of gas can be funneled directly into the core, triggering a final, furious burst of star formation. In this last stellar firestorm, the galaxy consumes its remaining fuel in one glorious, unsustainable binge, leaving nothing for the future. Tracking this missing gas is a detective story on a universal scale. Clues are found in the faint, X-ray glow of hot gas halos surrounding massive galaxies, and in the even more diffuse plasma that fills entire clusters. These observations point to a vast and complex cycle of baryonic matter, the ordinary material that makes up stars, planets, and us. Gas is not always destroyed, it is often just transformed, moved, or hidden, its journey marking the final transition of a galaxy from a living entity to a silent resident of the graveyard. This transformation of the universe is written in the light of distant clusters. In the 1970s, astronomers Harvey Butcher and Augustus Oemler pointed their telescopes at galaxy clusters incredibly far away, which also means they were looking deep into the past. What they found was startling. Those ancient clusters, as they existed billions of years ago, were not the red and dead cities we see in our modern cosmic neighborhood. They were brimming with blue, star-forming galaxies, vibrant with youthful energy. This phenomenon, now known as the Butcher-Oemler Effect, reveals a universe in dramatic transition. It tells us that the Great Migration into the interstellar graveyard has been a dominant theme of cosmic history. The processes of galactic death were not just occasional tragedies, they were a widespread epidemic in the younger universe, systematically quenching countless galaxies. As clusters aged and grew more massive, their dense environments became perfect engines for galactic sterilization. Ram pressure stripping, galaxy harassment, and the violent trigger of mergers worked overtime, efficiently shutting down star formation on a colossal scale. The blue galaxies Butcher and Oemler observed were in the process of crossing that great divide, their vibrant light destined to fade to red as they joined the silent majority. This effect provides a powerful snapshot of the graveyard under construction. It shows us that the quiet, retired universe we see around us today is the product of eons of cosmic violence and quiet fading, a slow-motion transformation that has shaped the entire population of galaxies. We are living in a relatively calm era, looking out at a graveyard that was filled to its capacity long ago. The environment a galaxy calls home is perhaps the single greatest predictor of its fate. It is a matter of cosmic geography, where the very neighborhood a galaxy resides in dictates whether it will live a long, vibrant life or face an early and violent end. Imagine two identical spiral galaxies born at the same time. One settles into a quiet, isolated region of space, a cosmic countryside we call the field. The other is drawn into the dense, bustling core of a massive galaxy cluster, a celestial metropolis. Billions of years later, their stories will be radically different. The field galaxy likely continues its gentle rhythm of star formation, while the cluster galaxy has almost certainly been quenched, its spiral arms faded, a red and dead citizen of the graveyard. This stark environmental dependence creates a map of cosmic life and death. The graveyards of the universe are not randomly scattered. They are overwhelmingly concentrated in these crowded, violent urban centers. The mechanisms of death here are relentless and varied. We have already met ram pressure stripping, the brutal galactic wind that scours away a galaxy's gas. But there is also a slower, more insidious process known as strangulation. In the dense environment of a cluster, a galaxy can be cut off from the fresh streams of cold gas that normally flow along the filaments of the cosmic web. Its external fuel supply is severed. The galaxy continues to form stars, but it is now living on a finite, internal reservoir. It slowly consumes its remaining gas until eventually it starves. This is a quieter end than a violent collision, but just as final. Adding to this chaos are constant gravitational interactions. In the cluster core, galaxies whip past each other at incredible speeds, their gravitational fields constantly tugging and distorting one another in a process called galaxy harassment. This relentless bullying shakes a galaxy to its core, disrupting the orderly orbits of its gas clouds and making the calm, sustained collapse needed for star formation nearly impossible. The cluster environment, with its combined forces of theft, starvation, and disruption, acts as a galactic killing field. It ensures that the most crowded places in the universe become, paradoxically, the quietest, filled with the silent, red remnants of galaxies that could not survive the urban chaos. Our own cosmic neighborhood is headed for a spectacular collision. The Milky Way, our home for billions of years, is on an inescapable trajectory toward the Andromeda Galaxy. In roughly 4 to 5 billion years, these two great spirals will meet. The initial encounter will be a slow, gravitational dance, a drawn-out pas de deux spanning hundreds of millions of years. Their mutual pull will warp and distort the familiar structure of both galaxies, stretching their spiral arms into long, luminous streams of stars. For a brief, brilliant period, this chaos will be a creative force. The violent compression of immense gas clouds will ignite a firestorm of new stars, a final, glorious burst of stellar birth. But this baby boom is a last gasp. The same collision will funnel catastrophic amounts of gas directly into the supermassive black holes at the hearts of both galaxies. Awakened, these monsters will flood the new system with energy, heating or blowing away the remaining star-forming fuel. As the merger completes, the two galaxies will coalesce into a single, new entity. The beautiful, ordered disk of the Milky Way will be gone forever, replaced by the random, swarm-like orbits of an elliptical galaxy. Astronomers have already named this future giant Milkomda. This new galaxy will be redder, older, and structurally simpler. Its star-forming days effectively over, it will begin its long, slow quenching, destined to cross the Great Divide and join the red sequence. Our galactic home, with all its star clusters, nebulae, and spiral grandeur, is fated to become a silent, red citizen of the interstellar graveyard. This is not a speculative doom, but a predictable astronomical forecast. It offers a humbling perspective, framing the entire vibrant night sky not as a permanent fixture, but as a fleeting, beautiful chapter in a much longer story of cosmic decline. Detecting these silent giants across the vastness of space requires a kind of cosmic forensics. Astronomers do not simply point a telescope and see a galaxy labeled as dead. They must read the story written in its light. This is done through massive sky surveys, projects that methodically scan the heavens, cataloging the positions and properties of millions upon millions of galaxies. The most crucial clue lies in a galaxy's spectrum, the unique fingerprint obtained by splitting its collective starlight into a rainbow of constituent colors. This spectrum holds the definitive signature of a galaxy's age and vitality. A young, star-forming galaxy shows bright, sharp emission lines. These are the brilliant beacons of energized gas, the telltale glow of vast nebulae where new stars are blazing to life. In stark contrast, the spectrum of a dead galaxy tells a quieter, older story. There are no bright emission lines. Instead, the spectrum is dominated by the broad, dark bands of absorption lines. These are the shadows cast by the atmospheres of countless ancient, cooler stars. They are the collective signature of a stellar population that has long since settled into a quiet retirement, with no young, hot stars left to illuminate the surrounding gas. By analyzing these spectral fingerprints, astronomers can take a census of the interstellar graveyard. They can distinguish the vibrant hum of a living galaxy from the deep, resonant silence of a dead one, not just in our local universe, but across billions of light years, peering back to a time when these cosmic giants were first beginning to fade. Yet the graveyard holds one final, surprising secret. Some of these so-called dead galaxies are not entirely silent. Advanced telescopes have peered into the hearts of these red giants and found faint, unexpected whispers of new life. A small but significant number show telltale signs of residual star formation, often concentrated in their very centers. It is as if a long dormant volcano has given a single, small puff of smoke. This discovery fundamentally blurs the line we thought separated living galaxies from dead ones. The interstellar graveyard may not be a final resting place after all, but perhaps a stage for a rare and limited cosmic resurrection. How is this possible? The mechanisms are as subtle as they are fascinating. Sometimes a small, gas-rich dwarf galaxy will stray too close and be consumed by the larger, retired giant. This minor merger provides a tiny, fresh supply of fuel, just enough to spark a final, isolated burst of stellar birth in the galactic core. In other cases, the galaxy's own vast, hot halo of gas may manage to cool in a small, localized region, allowing a trickle of cold gas to rain down onto the center and ignite new stars. This is not a return to vibrant youth. The galaxy does not suddenly regrow spiral arms and become a blue, star-forming powerhouse. The rejuvenation is feeble and fleeting, a brief flicker in an otherwise darkening sky. But its very existence changes everything. It tells us that galactic death is not always a permanent state. The forces that govern these cosmic giants are more complex and more forgiving than we ever imagined, offering a glimpse of unexpected activity deep within the quietest realms of space. The cosmic web is the ultimate source of life and death for galaxies. Think of it not as a static map, but as a living, breathing circulatory system for the entire universe. Invisible filaments of dark matter stretch across the incomprehensible voids, forming a vast, three-dimensional lattice. Flowing along these hidden rivers are immense quantities of primordial hydrogen gas, the raw material for building stars. For a galaxy, staying connected to this network is a matter of survival. When a galaxy is properly linked, it receives a continuous, gentle rain of cold gas directly from the cosmic web. Astronomers call this process cold flow accretion. It is a quiet, efficient delivery service that fuels the ongoing birth of new stars, allowing a galaxy to maintain its vibrant, blue glow for billions of years. This is the universe's natural order, the way galaxies are meant to live, but this life-giving supply line is incredibly fragile. If a galaxy's journey through the cosmos pulls it into a dense cluster, the environment changes catastrophically. The space between galaxies in these clusters is not empty. It is filled with a superheated plasma, a thin but roiling soup of particles at millions of degrees. When a galaxy enters this inferno, the delicate streams of cold gas flowing from the cosmic web are instantly vaporized. The supply is cut off at its source. The galaxy is suddenly isolated, like a farm whose irrigation canals have been severed by a desert. It must now survive only on the fuel it has left in its internal reserves. This is the beginning of the end. The galaxy continues forming stars, but it is now living on a finite stockpile. It slowly consumes its remaining gas, its blue light gradually fading as the last stellar nurseries fall silent. The cosmic web, which once gave it life, has now become the architecture of its starvation, dictating its final place in the interstellar graveyard. While the giants capture our attention, the smallest galaxies face a far more delicate existence. Dwarf galaxies, the cosmic equivalents of tiny villages, follow their own heartbreaking path into the graveyard. Their low mass and weak gravity make them exceptionally fragile, and their ultimate fate is almost entirely dictated by their surroundings. In the violent heart of a galaxy cluster, a dwarf galaxy is utterly defenseless. It can be stripped so completely of its gas and dark matter that it transforms into a ghost. These are the ultra-diffuse galaxies, vast, wispy collections of ancient stars that are so spread out they are almost transparent. They drift through space like cosmic jellyfish, their substance stretched to the point of near invisibility. In more extreme cases, a dwarf galaxy does not even get to keep its form. The relentless gravitational tides of the cluster can tear it apart entirely, scattering its stars into the general glow of intra-cluster light, erasing its identity forever. But a quiet neighborhood offers no real safety either. For the smallest dwarfs, the most decisive event may have happened in the universe's infancy, during the Epoch of Reionization. When the first stars and galaxies ignited, their intense ultraviolet radiation flooded the cosmos, heating the sparse gas that filled the voids. For a massive galaxy, this was a minor inconvenience. But for a tiny dwarf with weak gravity, this was a catastrophe. The gentle heating was enough to prevent its meager gas reserves from ever collapsing to form stars in the first place. Many of these small galaxies were stillborn, destined from the beginning to be faint, dark matter-dominated fossils. The story of these diminutive galaxies underscores a profound truth about the cosmos. The journey to the graveyard is not one single road, but a network of paths, each shaped by a galaxy's inherent strength and the unforgiving character of its environment. Magnetic fields weave an invisible web throughout the cosmos, a subtle force guiding the final breaths of galaxies. While gravity commands the grand movements, these fields act on a finer scale, influencing the fate of the very gas that gives a galaxy life. They are the cosmic choreographers of interstellar material, directing how gas flows, collapses, and even how it escapes. Within a galaxy, magnetic fields can provide a supporting structure for vast clouds of gas, helping them resist the violent turbulence that might otherwise tear them apart before stars can form. Yet this same supportive role can also stifle star birth. By adding pressure and stability, magnetic fields can prevent a gas cloud from fragmenting and collapsing under its own weight, effectively putting a gentle brake on the formation of new suns. This delicate balance means that a galaxy's own magnetic personality can either extend its vibrant life or nudge it more quickly toward retirement. The influence extends far beyond the galaxy itself. In the superheated plasma that fills galaxy clusters, magnetic fields are tangled throughout the intracluster medium. Here, they can act as a confining mesh, helping to hold this scorching gas together. This magnetic confinement can actually intensify the effects of ram pressure stripping. When a galaxy rams through this magnetized plasma, the fields can grip its gas more effectively, making the stripping process even more efficient at robbing the galaxy of its future. While their effects are subtle compared to the raw power of gravity, these invisible fields are a critical part of the story. They are one of the final pieces in the puzzle, a pervasive influence that helps shepherd gas on its journey, ultimately determining whether it becomes a brilliant new star or is lost forever to the darkness of the interstellar graveyard. The clock of cosmic death ticks at wildly different speeds. For a massive galaxy plunging into a dense cluster, the end can be shockingly quick. The brutal forces of ram pressure stripping and violent gravitational interactions can quench its star formation in a mere few 100 million years. On the scale of a galaxy's multi-billion-year life, that is a sudden, violent demise, a swift execution in the heart of a celestial metropolis. Yet for another galaxy, one drifting in the profound solitude of a cosmic void, death is a drawn-out whisper. Its quenching is a slow, relentless fade, a process of gentle exhaustion that can stretch across billions upon billions of years. This galaxy does not get robbed of its fuel. It simply lives a long, quiet life, slowly burning through its finite reserves until the very last ember of star formation finally winks out. This vast range of timescales means the interstellar graveyard is never a static collection. It is a dynamic, ever-changing city of the dead, continuously welcoming new residents. Some arrive abruptly, their vibrant blue light extinguished in a cosmic blink. Others drift in over eons, their glow reddening so gradually that the transition is almost imperceptible. Each galaxy carries the story of its death in its pace of decline. A rapidly quenched galaxy might retain some of its spiral structure, frozen in a red state like a cosmic fossil. A slowly faded one might see its arms blur and dissolve long before its final star is born. This diversity creates a rich tapestry of the deceased, a collection of endings as varied as the lives that preceded them. It forces us to ask what determines the speed of this final journey. Is it the galaxy's own mass, the violence of its neighborhood, or the hidden hand of its central black hole that sets the timer on its existence? Every star in a dead galaxy holds a chemical memory of its former life. These ancient suns are not just points of fading light. They are cosmic historians, their very atmospheres encoding a permanent record of the galaxy's vibrant past. This record is written in the language of elements. Inside the nuclear furnaces of stars, simple hydrogen and helium are forged into heavier atoms like carbon, oxygen, and iron. When massive stars die in supernova explosions, they scatter these newly created elements back into space, enriching the galactic gas from which the next generation of stars will form. A galaxy's history is therefore etched into the chemical composition of its stellar population. Think of it like tree rings, where each ring tells a story of the weather conditions for that year. In a galaxy, the specific mix of elements found in its stars reveals the intensity and duration of its star-forming era. A galaxy that lived fast and died young, quenching its star formation in a sudden, violent event, will have a very distinct chemical signature. Its stars will show an abundance of alpha elements, like oxygen and magnesium, which are produced rapidly in short-lived, massive stars. but they will be relatively poor in iron, an element that accumulates more slowly over time from the explosions of white dwarfs. The chemical fingerprint is one of a life cut short, a story abruptly interrupted. In contrast, a galaxy that faded slowly over many billions of years, gradually exhausting its fuel, will have a more balanced chemical makeup. Its stars will show a higher ratio of iron to alpha elements, because the galaxy had enough time for countless generations of smaller stars to contribute their iron-rich ashes to the galactic ecosystem. This slow fade produces a richer, more complex chemical tapestry. By analyzing the faint light from these distant red suns, astronomers perform a kind of galactic archaeology. They use powerful spectrographs to split the starlight, reading the deep, dark absorption lines that reveal which elements are present and in what quantities. Each spectrum is a chemical tombstone, telling us not just when the galaxy died, but how it lived. We can decipher whether it experienced a single, glorious burst of star formation or a long, sustained period of gentle stellar birth. This chemical legacy transforms the interstellar graveyard from a collection of silent fossils into a vast, readable library, its shelves lined with the autobiographies of galaxies that are no more. At the very heart of a galaxy cluster, a cosmic monarch reigns supreme. This is the CD galaxy, a supergiant elliptical that dominates its celestial city not through peaceful rule, but by cannibalizing its subjects. Galactic cannibalism is the ultimate expression of cosmic hierarchy, a brutal process where the largest galaxy grows even more massive by consuming its smaller neighbors. The gravitational pull of the central giant is so immense that it relentlessly draws in passing dwarf galaxies and even fellow ellipticals. These smaller systems do not simply orbit, they are torn apart. As a victim galaxy approaches, the overwhelming tidal forces stretch it into long, luminous streams of stars, ghostly tendrils that are slowly siphoned into the CD galaxy's vast halo. Within a few 100 million years, the smaller galaxy's identity is completely erased, its stars and gas absorbed into the body of the giant. This is not a merger of equals, but a complete and total digestion. The cannibalized galaxy is unmade, its structure dissolved, its future extinguished. The central monster grows fatter on this stellar diet, becoming the brightest and most dominant feature in the cluster, a king built upon the graves of its rivals. But the consequences of this feast ripple far beyond the monarch's borders. The influx of fresh gas from the consumed galaxies often triggers a cataclysmic response. It funnels directly into the CD galaxy's supermassive black hole, awakening it into a ferocious active galactic nucleus. The resulting outburst floods the entire cluster with intense radiation and powerful jets. This energy acts as a cosmic regulator, heating the gas throughout the cluster environment and preventing any other galaxies from forming new stars. In a cruel twist, the act of cannibalism by the central galaxy helps to quench star formation across its entire domain, ensuring the cluster remains a sterile graveyard. This process is a fundamental driver of hierarchical growth in the universe, proving that the largest structures are built from the ruins of the small. It is a stark reminder that in the deep reaches of space, even galaxies are not safe from being consumed by a hungrier neighbor. Peering into the interstellar graveyard means searching for ghosts. These retired galaxies emit a faint, ruddy glow, the combined light of countless ancient stars, each one a dim ember compared to the brilliant blue infernos of youthful suns. This inherent dimness is the first great challenge for astronomers. A dead galaxy's light is easily lost, drowned out by the glare of its brighter, active neighbors, or simply blurred into the general background haze of the night sky. It is like trying to spot a single, cooled coal in a distant, dark field, while nearby bonfires blaze and distract the eye. The second, even greater challenge is time itself. To truly understand how a galaxy dies, we cannot simply look at the graveyard around us. We must witness the deaths as they happened across the universe's long history. We need to see these galaxies not just as they are now, but as they were billions of years ago, right as they were entering their final, quiet state. This requires looking back in time, a feat only possible because light takes time to travel across the cosmos. When we observe a galaxy 10 billion light-years away, we are seeing it as it was 10 billion years in the past. Capturing the faint light from these incredibly distant, dying galaxies demands the most powerful eyes humanity has ever built. The Hubble Space Telescope, peering primarily in visible light, began this deep time census, revealing the early universe was far more active and chaotic than we ever imagined. But Hubble could only see so far. The James Webb Space Telescope, with its infrared vision, is the ultimate tool for this cosmic archaeology. Infrared light pierces through cosmic dust and is naturally emitted by these old red stars, allowing Webb to see the faintest, most distant retirees in stunning detail. It is effectively a time machine, uncovering the very first galaxies to ever fade away. Without these technological marvels, the graveyard would remain a silent, invisible mystery. Every faint smudge of red light they capture is a data point, a clue in the grand detective story of how the universe grows old and quiet. The ultimate test of our understanding lies not just in observation, but in creation. To truly decode the interstellar graveyard, we must build our own universes inside supercomputers. These are cosmological simulations, vast digital realms where the laws of physics are programmed to run forward over billions of virtual years. Projects with names like Illustris TNG and EAGLE are not simple animations. They are complex mathematical engines, starting with a near-uniform soup of dark matter and gas in the early universe, and then letting gravity and other forces sculpt that chaos into galaxies. The goal is breathtakingly ambitious: to see if our theories can spontaneously give birth to the cosmic graveyard we see outside our telescopes. The challenge is immense, for these models must balance a universe of competing forces. They must account for the relentless pull of gravity, which draws matter together into the cosmic web. They must simulate the complex hydrodynamics of gas, how it flows, heats, and cools. They have to program in the rules for star formation, deciding when a dense cloud of virtual gas should collapse into a new sun. And most critically, they must include the explosive feedback from supermassive black holes, those galactic thermostats that can heat or expel a galaxy's lifeblood. When these simulations run, they generate not just one galaxy, but millions, each with its own unique history of birth, life, and death. The true measure of success is whether this synthetic universe, after 13 billion virtual years, ends up with a clear division between the blue cloud of star-forming galaxies and the red sequence of the dead. Do these digital realms fill their clusters with quenched red giants while leaving a few blue spirals in the voids? The answer is a qualified yes. The most advanced simulations do, in fact, reproduce the large-scale structure of the interstellar graveyard with remarkable fidelity. But the failures are just as instructive as the successes. Sometimes, a simulation might produce too many massive, dead galaxies too early in cosmic history. This tells theorists that their model for black hole feedback is perhaps too efficient, too brutal. Another simulation might struggle to create the very densest red nugget galaxies, hinting that some early, rapid process of galaxy formation is still not quite captured in the code. Each discrepancy is a clue, It forces scientists to re-examine their assumptions about the fundamental physics that governs galactic life and death. These virtual graveyards are our proving grounds, allowing us to run cosmic experiments we could never perform in reality. They let us watch over and over again the precise moment a galaxy's star formation is quenched, tracing the chain of causality back to its source. In this way, the silent, red galaxies in our telescopes and the glowing pixels in a supercomputer are in constant dialogue, each refining our story of how a universe full of light gradually, inevitably grows quiet. This final journey into the graveyard reveals a force even more profound than black holes or galactic collisions. The ultimate architect of cosmic silence is dark energy, the mysterious presence driving the universe's accelerating expansion. While gravity pulls matter together, dark energy works in opposition, pushing the very fabric of space apart. Its influence is slow but utterly inexorable, and it dictates the final chapter for every single galaxy. As the expansion accelerates, the cosmic web itself will begin to fray. Those invisible filaments of dark matter that channel life-giving gas will stretch and grow thin, like a vast network of rivers slowly drying up in a deepening drought. The gentle rain of cold gas upon galaxies, the process that has fueled star formation for billions of years, will first become a trickle and then cease entirely. Every galaxy, regardless of its current environment, will become an isolated island. The great metropolis of galaxy clusters will not collapse, but they will grow dark, their residents long since quenched and now drifting ever farther apart. In this far future, the vibrant blue cloud of star-forming galaxies will vanish completely, its last member having crossed over into the red sequence. Star formation will end everywhere. The universe will no longer have a few scattered graveyards. It will become one, a single, vast, and dark interstellar graveyard where the only light comes from the dim, red embers of the last dying stars. Quiet retirement we observe today in distant clusters is not a local anomaly. It is a preview, a glimpse into the ultimate fate of the entire cosmos, a time when the universe itself grows old, cold, and silent. The hunt for the universe's first deceased galaxies has begun in earnest. With the James Webb Space Telescope now operational, astronomers are peering further back in time than ever before, scanning the cosmic dawn for signs of the very first stellar civilizations to rise and fall. Their goal is to find primordial galaxies that lived fast and died young, quenching their star formation when the universe was a mere infant. Discovering these ancient relics would be a monumental breakthrough, forcing us to rewrite the entire timeline of cosmic life and death. How quickly could a galaxy assemble itself and then shut down in those chaotic early years? The existence of such early retirees would tell us that the forces of galactic death, particularly the feedback from supermassive black holes, were operating with shocking efficiency and speed in the primordial universe. It suggests that the first black holes grew to immense sizes with incredible haste, unleashing energies powerful enough to sterilize their entire galactic homes almost immediately. Finding one of these galaxies would be like uncovering the ruins of a lost civilization that flourished and collapsed while the rest of the world was still being settled. It would reveal the ultimate limits of early star formation, showing us just how brief and brilliant a galaxy's youth could be before the cosmic killers weaved their first silent graveyards in the dark. These galactic undertakers each have a distinct method of operation, a signature written in the fading light of their victims. The first, ram pressure stripping, is a ruthless cosmic mugger. It ambushes a galaxy as it speeds through the crowded core of a cluster, where the space between galaxies is filled with a superheated plasma. This thin, searing gas acts like a hurricane-force wind, violently tearing the galaxy's own star-forming gas from its grasp. It is a direct and brutal robbery, leaving the galaxy gasping and impoverished in a matter of hundreds of millions of years. Then there is strangulation, a far more insidious killer. This is the slow poisoner, the one that cuts off the supply lines. A galaxy reliant on fresh gas flowing from the cosmic web can be severed from this life-giving source, often when it enters a dense environment. It is not robbed of the fuel it has, but is starved of any new fuel. The galaxy continues forming stars, living off its remaining internal reserves until it slowly, inevitably, exhausts every last drop. Its vibrant blue light fades to red over billions of years, a long, quiet suffocation. Perhaps the most tragic agent is the internal illness, the feedback from an active galactic nucleus. Here, the galaxy's own supermassive black hole, its very heart, turns against it. As the black hole feeds, it unleashes torrents of energy that flood the galaxy, heating the cold gas to millions of degrees. This scorching fever prevents the gas from ever cooling down to form new stars, or in more extreme cases, blows it clean out of the galaxy entirely. The galaxy is killed from the inside out, betrayed by the engine at its core. Finally, we have the catastrophic accident, the major merger. When two spiral galaxies of similar size collide, it is a spectacular but terminal event. The beautiful structures of both are violently erased, their gas funneled into a final, furious burst of star formation and a feeding frenzy for the central black holes. The resulting galaxy is often an elliptical, a red and dead giant whose identity was forged in a single, transformative crash. Identifying which of these undertakers is responsible for a specific galaxy's death is the work of cosmic forensics. Astronomers must become detectives, gathering clues across the entire electromagnetic spectrum. They look for the telltale signs of stripped gas trailing behind a galaxy, the specific chemical fingerprint of a slow strangulation, or the brilliant glare of a central black hole in its final, destructive feast. Each case is unique, a puzzle written in the light of a fading giant. Long before the great clusters and quiet voids took shape, the first light in the universe may have cast the first shadows of death. This was the Epoch of Reionization, a cosmic dawn so transformative it likely created the very first residents of the Interstellar Graveyard. In the universe's infancy, space was filled with a dense, neutral fog of hydrogen gas. Then the first stars and galaxies ignited, and their intense, searing ultraviolet radiation began to flood the cosmos. This radiation did not gently illuminate the fog. It violently tore it apart, stripping electrons from the hydrogen atoms in a process called ionization. This burned away the primordial mist, clearing the universe and making it transparent to light for the very first time. But for the smallest, most fragile structures taking shape in the darkness, this dawn was not a blessing, it was a catastrophe. Countless small clumps of dark matter were trying to gather their own clouds of hydrogen gas, hoping to become galaxies. They were the cosmic seeds of what could have been. Yet when the flood of UV light hit them, their fate was sealed. The radiation heated their sparse gas, giving its atoms just enough energy to resist the weak gravitational pull of their small dark matter halos. The gas could not cool down, it could not collapse, and it could never ignite into stars. These potential galaxies were doomed to be stillborn. They had all the necessary scaffolding of dark matter, but they were forever denied the spark of stellar life. They became dark, starless halos, phantom structures adrift in the young cosmos. This means the graveyard is far older and more haunting than we ever realized. It is not populated only by galaxies that lived and died, but also by ghosts, by the countless billions that never were, their cosmic potential extinguished before they could even draw their first breath of light. A subtle, ghostly light fills the immense voids between galaxies in the busiest clusters. This is intra-cluster light, the literal dust of the interstellar graveyard. It does not come from any single galaxy, but from countless stars that have been torn from their homes during violent encounters. When galaxies are pulled apart by tidal forces or collide in a catastrophic merger, their stars are not destroyed. Instead, they are flung into the emptiness, becoming a permanent, wandering population adrift in the space between galaxies. This creates a faint, almost imperceptible glow that permeates the entire cluster, a collective phantom of all the galactic structures that have been dismembered over billions of years. To detect this light is an incredible challenge. It is millions of times fainter than the darkest night sky we see from Earth, easily washed out by the brilliant glare of the cluster's remaining galaxies. Astronomers must use the most sensitive telescopes and sophisticated image processing to subtract the light from every known object, revealing the leftover, ethereal haze that remains. This faint glow is more than just a cosmic curiosity. It is a fossil record of the violence that has shaped the cluster. By measuring the total amount of intra-cluster light, scientists can essentially weigh the total mass of stars that have been stripped from their galaxies throughout cosmic history. This provides a direct measure of the destructive processes that have filled the graveyard, offering a census of the dead not by counting silent galaxies, but by collecting their scattered remains. The very existence of this light confirms that the graveyard is not just a collection of intact retirees, but also a realm of the utterly dissolved, where entire galactic identities have been erased and their starlight spread thin across the cosmos. But what becomes of the planets when their galaxy fades? As a galaxy enters the graveyard and its star-forming engines fall silent, a profound stillness settles over its countless solar systems. No new worlds will ever form again, for the great cosmic factories that forge the elements for rocky planets and the icy seeds for gas giants have shut down permanently. The existing planetary systems, however, remain, each one now locked into its own slow, individual countdown. For a time, life may continue on worlds orbiting long-lived, stable stars. But the universe has turned off the lights in the nursery, and this is a final, irreversible change. The vibrant era of cosmic creation is over for this galaxy, leaving behind only the long, slow process of decay. Every star, from the smallest red dwarf to the most massive blue giant, is now a closed system with a finite future. They will continue to burn through their fuel, but when they are gone, there will be no replacement. The galaxy's stellar population is fixed, a collection of embers that will cool one by one across timescales so vast they defy human comprehension. This transforms the interstellar graveyard into something even more profound, a frozen museum of stellar systems, each exhibit slowly fading toward the same inevitable darkness. The fate of every planet is now tied to the life and death of its parent star, a dependency that will ultimately seal the destiny of every world, including those that may have once blossomed with life. Over trillions of years, the brilliant main sequence stars will exhaust their hydrogen fuel. Sun-like stars will swell into red giants, their fiery outer layers engulfing and incinerating the inner planets before collapsing into dense, Earth-sized white dwarfs. Any surviving outer worlds will be left orbiting a cooling stellar cinder, their surfaces growing colder with each passing eon. More massive stars will end their lives in supernova explosions, cataclysmic events that can vaporize entire planetary systems or, at the very least, sterilize any orbiting worlds. The remnants of these violent deaths, neutron stars and black holes, will become the new anchors for any surviving planets, casting them into a perpetual, frozen night. The slowest burning stars, the red dwarfs, will shine on for tens of trillions of years, but even their feeble light will eventually flicker and die, leaving behind cold, dark dwarfs. In this unimaginably distant future, every planetary system in the graveyard will be a frozen relic. Atmospheres will condense and fall as snow, oceans will freeze solid to the bedrock, and the very rotation of planets may slow to a halt. The graveyard thus becomes a silent archive, a cosmic library where the records of countless worlds are preserved in deep freeze. It is a haunting thought that among these frozen archives could be the remains of civilizations that once looked up at their galactic sky, unaware that their entire universe was gradually, inexorably growing dark. Our very existence is a direct product of cosmic timing. We live in a galaxy that is still alive, still breathing, a place where new stars are forged from the interstellar medium. This vibrant activity was not just a backdrop for our formation, it was an absolute prerequisite. Every element essential for life, from the carbon in our cells to the iron in our blood, was cooked in the heart of a long-dead star and scattered into space by a supernova explosion. That material then became part of a new generation of stars and planets, including our own. This chain of events requires a dynamic, star-forming galaxy, one that is actively recycling its gas and dust. A galaxy in the graveyard has ended this cycle. Its stellar factories are closed, its gas reserves exhausted or sterilized. It is a cosmic retirement home where no new planets are born, and the existing ones orbit dying stars. This simple, profound fact connects the fate of galaxies to our own presence here as observers. It touches upon a philosophical idea known as the Anthropic Principle. In its most basic form, this principle suggests that the universe we are able to observe must, by necessity, have properties that allow for our existence. We could not possibly find ourselves in a galaxy that has already faded into the graveyard, because such a place could not have produced us. The interstellar graveyard represents a state of the cosmos that is, by its very nature, uninhabitable and utterly unobservable by beings like us. It is a future so bleak and empty that no conscious mind will ever be there to witness it. This makes our own galactic home, the Milky Way, a special place not just in space but in time. We reside in a narrow window of cosmic vitality, a golden age of star formation that made our world possible. Our entire history, from the first single-celled organism to the civilization gazing at the stars, is unfolding during our galaxy's active life, a fleeting moment before its own long, slow journey into the quiet and the dark. Even with all we have uncovered, the interstellar graveyard guards its deepest secrets. The precise sequence of events that leads to a galaxy's final quenching remains a tangled puzzle. Does a black hole's outburst always come first, or can a galaxy be stripped of its gas by a cluster, only to have its central engine awaken in a final, futile protest? We do not yet know how the various feedback mechanisms interact, compete, or even collaborate to extinguish a galaxy's light. Is it a single, decisive blow or a death by 1,000 cuts? These are the questions that propel the next generation of astronomical discovery, fueling missions designed to witness cosmic death in real time. The Nancy Grace Roman Space Telescope, with its incredibly wide field of view, will perform a vast census of the cosmos, mapping the distribution of galaxies and dark matter with unprecedented detail. It will find millions of galaxies in the act of quenching, allowing us to compile a definitive timeline of their final days. Meanwhile, from the high deserts of Chile, the European Extremely Large Telescope will turn its massive 39-meter eye toward the most distant of these fading giants. Its unparalleled sharpness will pierce through the cosmic dust, revealing the intricate structures within galaxies as they transition from blue to red, showing us the exact moment a supermassive black hole flares to life or a spiral arm's glow begins to dim. These observatories will work in concert, one providing the grand statistical story of galactic death across the universe, and the other delivering intimate, high-resolution portraits of the final moments. They are not just tools, they are time machines built to watch the graveyard fill across billions of years. The quest to understand this great silence is far from over, and the answers we find will ultimately tell us how every brilliant island of stars, including our own, meets its end. This grand cosmic cycle gives the universe its deep, textured history. From the first chaotic clouds of hydrogen gas to the majestic spirals we see today, every galaxy is a character in an epic story of creation and decay. The forces we have witnessed, from the internal betrayal of a supermassive black hole to the environmental violence of a galactic cluster, are not random acts of destruction. They are the fundamental, predictable mechanisms that guide the universe from a state of brilliant, youthful chaos toward one of profound, ordered quiet. Our own Milky Way is not a spectator to this drama, but a participant with a role already written. Its future collision with Andromeda and its eventual fade into the red sequence are not speculative fates, but the next chapters in a story that has been unfolding for over 13 billion years. When we gaze at the night sky, we are not looking at a static, eternal tapestry. We are seeing a single frame in a cosmic film of unimaginable scale, a fleeting moment of vibrant light before the long, slow fade. The interstellar graveyard is not a distant, abstract concept. It is the ultimate destination for every island of stars, a silent testament to the universe's relentless and beautiful evolution. It urges us to look deeper, to question further, and to cherish the brief, brilliant era of cosmic life that allows us to witness it.